Hey, what's up guys, welcome back to Eureka, and in this video we're going to be talking about the thermal properties of matter in chapter 1 of physics level M. So, what do we mean by thermal properties of matter? We mean things like the latent heat of fusion or vaporization, or how to calculate the heat when 1 kilogram of some substance increases its temperature by 2 degrees Celsius, for example. We'll go over all of these things in detail in this video. So sit back, relax, and enjoy the show. Suppose we have a system we have a container of gas particles, or liquid, or solid, or anything, but let's just use this as an example. We have particles in a system at, say, 50 degrees Celsius. Alright? Now, what happens if we add heat with a flame? I have this container of particles of some substance, and suppose I have a flame. How do you do a flame? Suppose inside this, I don't know, I'm not an artist, but this is supposed to be a flame, okay, if you don't mind. This is a flame, and suppose this flame supplies heat to the gas or substance in question, okay? So, when we add heat, our kinetic energy of the particles increases, and so the temperature increases. So, we can derive that the kinetic energy of the average kinetic energy of the particles is directly proportional to the temperature. But be careful, this temperature is measured in kelvins and not degrees Celsius, okay? Because if you draw the graph, when it's kelvins, it passes through the origin, but when it's Celsius, it will be shifted in some way. So just the first basic rule of the day: whenever you add heat to a system, the temperature increases proportionally to the kinetic energy. It's proportional. This is a proportionality symbol to temperature, okay? This is the key to unlocking everything in this chapter. So now let us redefine temperature in a more conventional way. So, what is temperature? We define temperature as the measure of hotness, right? But what is hotness? If we add heat to the particles, they move faster, and thus the temperature increases. As we said, temperature increases when we add heat. But why does the heat increase in temperature? Because the particles move faster and their kinetic energy increases. So the more scientific definition of temperature is that temperature is actually a measure of the average kinetic energy. So our definition of temperature is the measure of the average kinetic energy of the molecules of the substance in question. Alright? But this does not mean that temperature is kinetic energy. No, that's completely false. You can think of it like this. Kinetic energy is measured in joules, right? We add joules to a system, and then its temperature increases. Suppose, to give an easier analogy of this, suppose you have wealth, like you have a lot of money, yeah? This is money. Anyway, and this is your money, okay? Like you have a vault or whatever, and the kinetic energy, the heat, is adding to your wealth. So temperature is like wealth, and the heat or kinetic energy heat is like the money. Yeah, it's basically, if you add money to wealth, it's the same thing as adding heat to temperature. The relation between heat or kinetic energy and temperature is the same as that of money to wealth. Just an easier way to understand. You add heat, you gain temperature. Alright? We end this part of the session by saying that we always need heat energy to increase temperature. Right? Like we said with money and wealth. Okay? So now we move on to the actual difficulties of the chapter. Suppose you have a system of water, for example, and you're either heating it or cooling it, and we will not discuss state changes like ice or water till now because they have special cases, but just suppose you have water, only liquid water, and we're trying to heat it or cool it and play with the energy involved. We're going to explain this now. So, what is the specific heat capacity? Capacity of some substance. We denote specific heat capacity by small c. Okay? So we know that C is the specific heat capacity. But what is specific heat capacity? It is the energy required to raise the temperature of 1 kilogram of a substance by 1 Kelvin. Now, what does this mean? Obviously, if I have 1 kilogram of water and 2 kilograms of water, I'm going to need twice the energy from the 1 kilogram to heat it than the 2 kilogram, right? The 1 kilogram will require half as much heat as the 2 kilogram, right? And if I have 1 kilogram and I want to heat it by 5 Kelvin, this will be 5 times as much as 1 Kelvin, okay? So C helps us get a easily quantitative measure of the amount of heat needed per 1, so that we can easily calculate heat involved with any change of temperature. It is measured in joules per kilograms dot Kelvin. If we have C is equal to 1 joule per kilogram Kelvin, it means I need 1 joule to raise 1 kilogram by 1 Kelvin. And if we have, for example, 2 joules, I need 2 joules to raise 1 kilogram by 1 Kelvin, okay? This is usually given in a question, and you do calculations around it. If Q is measured in joules, and we want to find Q, but we only have C, and C is in joules per kilogram Kelvin. How do we turn joules per kilogram Kelvin into joules only? When we multiply by mass in kilograms, we can cancel the kilograms, okay? And when we multiply by the change in temperature, because it differs with the change in temperature, this will be in Kelvin, and these two can cancel. So we use proportionality and get the formula Q is equal to MC delta T. We read this as the amount of energy needed to raise, the amount of energy needed to heat a substance of some certain mass by a certain temperature is equal to the mass times the C, specific heat capacity, times the temperature, okay? Now this might be confusing at first, but with applications we can do this. Just one more easy analogy. If I have 1 joule per kilogram Kelvin No, let's not change it. Let's not make it 1. Let's make it like 20. If I have a substance, let's call it substance X, and its heat capacity is this. If I want to heat 2 kilograms, it will obviously be twice the heat, 40 joules for 1 Kelvin. So this is where we did the relation from. Now, moving on, let's solve a quick example. If the heat capacity of water is 4.2 times 10 to the power of 3 joule per kilogram Kelvin, we need to find Q, the amount of energy needed to raise the mass of 10 kilograms by raise the mass units by 10 Kelvin. So if per kilogram per Kelvin I need this many joules to raise the temperature of water, how many joules do I need in total to raise 10 kilograms by 10 Kelvin? We apply the formula Q equals mc delta T. Q is equal to 10 times 4.2 times 10 to the 3 times 10, which will give us Q, that's a weird Q, is equal to 4.2 times 10 to the 5 joules. That is how you use this formula, and that is what specific heat capacity is. I really hope you understood that. Now, moving on to change of states, because when a substance changes from solid to liquid or liquid to gas, a specific case happens. Okay.